Right. So we are going to start the new lesson, that is homogeneous phase equilibrium. Right. When it comes to this homogeneous phase equilibrium, we are discussing about equilibrium between two phases, but those are in same physical state. Right. That is something like dissolution of iodine in between water and CCl4. Right, water and CCl4. Just suppose a situation where we have aqueous iodine, right? Aqueous iodine, right? What is the color of aqueous iodine? When you have iodine in water, this is brown in color. This is brown in color. What we are going to do? We are going to add CCl4 into this. We are going to add CCl4 into this. Once you add CCl4, right? Once you add CCl4, what's happening? I'll just write CCl4 in blue color, right? And this is normal water, right? This is water layer, and this is CCl4 layer, right? You know that CCl4 has a higher density than water, therefore it's into the bottom, right? And in this, what happens? Our iodine will move into aqueous layer. Iodine in the aqueous layer will move into the CCl4 layer, right? Iodine in the aqueous layer will move into the CCl4 layer. Now what happens? This iodine is dissolved in between both CCl4 and water, right? Molecules of CCl4 moves into the aqueous, molecules of iodine in CCl4 layer moves into the aqueous layer, and the molecules in the aqueous layer moves into the CCl4 layer, right? So that happens, and what will happen? There will be an equilibrium in between them, right? There will be an equilibrium in between them. How these stuff are soluble? When you consider iodine, right? Iodine is a non-polar molecule, right? I2 is a non-polar molecule, right? So that iodine is like this. How about CCl4? CCl4 also non-polar. CCl4 also non-polar. So in between we have London dispersion forces. We have London dispersion forces. As a result, iodine is soluble in CCl4, right? And also when you consider iodine and water, the water molecule is polar, right? Water molecule is polar. So this is delta minus, these are delta plus, right? As a result, the electron cloud of iodine will repel towards the other side. So what happens? It will be an induced dipole, right? It will convert into an induced dipole. So it is soluble in water due to dipole, induced dipole. Right? Dipole, induced dipole attractions. It is soluble in water. Right? So as this is soluble in both, what will happen? There will be a iodine equilibrium in between water and CCl4. Right? So at first what happens? I2 in the aqueous layer move into CCl4. Right? Because initially in CCl4 you didn't have anything. Right? You didn't have anything. Right? And after some times, what will happen? The CCl4 layer contains iodine. Some molecules again try to come into the aqueous layer, right? So you get I2CCl4 moves into I2 aqueous. Move into I2 aqueous, right? As a result, what will happen? When the both rates are equal, we have a equilibrium between iodine aqueous and iodine CCl4, right? There's an equilibrium between iodine aqueous and iodine CCl4. Okay, so what is the color of iodine? Iodine in aqueous layer is brown, right? And iodine in CCl4 layer, it is purple, right? CCl4 layer, it is purple. right? So initially the entire solution is brown in color, but once you add CCl4, it will turn, the CCl4 layer slowly turns into purple, and the color of the brown color will fade, right? And we know that iodine is more soluble in CCl4 than water, right? Rather than this is more stronger when considering iodine. So what will happen? Most of the iodine will be there in the CCl4 layer, right? So having a equilibrium, right, between, right, having an equilibrium of solute in between two immiscible solvents is called phase equilibrium. What phase equilibrium? Homogeneous phase equilibrium, right? Homogeneous phase equilibrium, right? So we write that, just write. The phases involved in this sort of equilibrium, the phases involved in this sort of equilibrium, or you can write phases involved in homogeneous phase equilibrium, phases involved in homogeneous phase equilibrium are in same physical state, are in same physical state. Are in same physical state. Right? Write example. Example. Distribution of a solute. Distribution of a solute in between two immiscible solvents. In between two immiscible solvents. In two immiscible solvents. Just write example, right? That was a distribution of solute in between two immiscible solvents, right? Separate, right? When CCl4 is added into, when CCl4 is added into, when CCl4 is added into aqueous solution of iodine, aqueous solution of iodine, homogeneous phase equilibrium system is produced. Homogeneous phase equilibrium system is produced. Homogeneous phase equilibrium system is produced. Okay, right. So we go this one. Just write this one. Adding CCl4, it is brown in color, I2 aqueous. Then you get two layers get separated, right? And separately write these two also. Because of these two, it is soluble. Don't write the equations, right? Don't write the equations. Okay, right. After that, just write, right? Hope you wrote these stuff. Okay, right. Just write initially aqueous iodine molecules aqueous iodine molecules move into the CCl4 layer. Aqueous iodine molecules move into the CCl4 layer. With a higher rate, with a higher rate, and the rate decrease with respect to time. With a higher rate and rate decrease with respect to time. Next one. Next point. Iodine molecules in the CCl4 layer. Iodine molecules in the CCl4 layer will also start to move into the aqueous layer. Will also start to move into the aqueous layer with a lower rate, and the rate increase with respect to time. Rate increase with respect to time. Okay, right. Shall we write these two? No need of that. Just write the two black ones. Just write two black ones. Okay, two black ones. After that, right? When the rate of both reactions are equal, when the rate of both reactions are equal, the system reach the homogeneous phase equilibrium. System reach the homogeneous phase equilibrium of iodine in between of iodine in between water and CCl4. Water and CCl4. Right? Okay. Write the blue color equilibrium. Then if you just consider this, I'll draw a small graph here. This is time, this is concentration. Suppose the system reached the equilibrium at this point. Right? Initially, you have high iodine concentration in water, right? And it decreases with respect to time, and at a certain point, it will become constant. This is I2 AQ concentration, right? And when it comes to CCl4, initially nothing, but it increases with respect to time and will become equal. This is I2 CCl4, right? I did CCl4, right? So you need to understand that CCl4, iodine is more soluble in CCl4, right? As iodine is more soluble in CCl4, right? It has a higher concentration at the end. It has a higher concentration at the end. Okay, right. Quick write that. Write the subtitle, Nernst distribution law. Nernst distribution law. N-E-R-N-S-T. Nernst distribution law. Right. Now what this Nernst distribution law says, right? When you have a common solute, right? When you have a common solute dissolved and distributed in between two immiscible solvents at constant temperature, right? When a common solute, let's say I2, this is aqueous, this is I2 CCl4, right? When a common solute dissolved and distributed in between two immiscible solvents, right? This is CCl4 and this is water, right? It is dissolved and distributed in between two immiscible solvents. What happens? The concentration ratio is constant, right? The concentration ratio, that is I2CCl4 divided by I2AQ. This concentration ratio, right? This is a reaction between I2 aqueous has an equilibrium between I2 CCl4, right? So what it says, the concentration ratio of the solute in between two solvents is constant. This is called Kd, right? That is known as what? Kd, right? So what is this Kd? Kd is distribution coefficient of I2 between, this part is really important, CCl4 and water, right? Distribution coefficient of iodine between CCl4 and water, right? So if you say CCl4 and water, I2 CCl4 concentration comes top, water bottom. If we say, right, if we say between water and CCl4, right? If we say between water and CCl4, we write our Kd is equal to I2 aqueous concentration over I2 CCl4. Understood? Right? It is not because of the equation, it is because of the what we have written here. If it is CCl4 and water, that is this. Right? But if we say between water and CCl4, you are writing it like this. Okay? So I want you to write this one separately, right? Just to get some idea what is going on here. Okay? When you are writing, not now. When you are writing. Okay? Right. Write the one Nernst distribution law. Nernst distribution law. Okay? That is this, right? When a solute is dissolved and distributed, when a solute is dissolved, distributed, when a solute is dissolved, distributed, and is at equilibrium, in between two immiscible solvents, at constant temperature, the concentration ratio of the solute in two solvents, is constant. Okay, is constant. Right. Got it? We'll write this one and then this one. This is the explanation, and this one separately, right? This one separately, because you need to understand that if you say it like this, it is this. What you say first comes on top. Okay? Right. Right. Write the subtitle: Problems involving Nernst distribution. Right. Subtitle: Problems involving Nernst distribution. No. Before that, we need to write some important points. Right. So when you consider this Nernst distribution, right? When you consider this Nernst distribution, we need to satisfy some conditions that to apply this KD value, right? In order to apply this KD, we need to satisfy these conditions. Okay. So therefore, after this one, write important points, right? Just write important points. Important points. First one, KD only depends on temperature. KD only depends on temperature. Right? Important points, right? Not the problems, important points. First one, KD only depends on temperature. KD only depends on temperature. Second one, in order to apply the Nernst distribution law, the system should satisfy the following conditions. The system should satisfy the following conditions. System should satisfy the following conditions. Okay, first one, the solute must dissolve, distributed and solute must dissolve, distribute and has to be at equilibrium in between. Solute must dissolve, distribute and has to be at equilibrium between the two solvents. Has to be in two solvents. Second one, the solute has to be in same molecular form, solute has to be in same molecular form in both solvents. Same molecular form in both solvents. Same molecular form in both solvents. Right. So this is what happens. Now when you consider CH3COOH, CH3COOH is like this, acetic acid, right? So when you add acetic acid into water, right, it will be there like this. It will be there like this because this part is polar and water is also polar. It will readily dissolve, right? But there's a problem when you add this one into something like CCl4. When you add this one into CCl4, as CCl4 is completely non-polar, the polar COOH part cannot dissolve. In order to overcome that problem, right? In order to overcome that problem, what happens? This particular CH3COOH molecule would dimerize like this through hydrogen bonds, right? Through hydrogen bonds, they will dimerize, right? So what happens? It looks like this is something else. No? It looks like this is something else. It is not in the same molecular format, right? This is just CH3COOH, and this is like CH3COOH twice. It will dimerize, right? So can we apply Nernst distribution law here? No, right? This is at equilibrium, of course, right? At constant temperature, this is at equilibrium, but we can't apply Kd into this one, right? Because it is not in the same molecular form. Understood? Right. Just right. Right? Yes, right. Therefore, Nernst distribution law cannot apply. Nernst distribution law cannot apply for the following system. For the following system. Right? For the following system. Right? Just write this one. Right? You know about this one, right? We have learned this stuff in bonding, organic chemistry, and everywhere we have learned that this happens, right? Therefore, just write this one. You can understand. Okay. Right. Then Write the subtitle: Problems involving Nernst distribution. Problems involving Nernst distribution. Right? Problems involving Nernst distribution. Right? Problems involving Nernst distribution. Right. Now, write this question. Right. So, one by one, we'll discuss questions. Right. Here, actually, in this part, there's no more theory at all. Right. No more theory at all. The only theory is that is Kd is equal to concentration of the solute in one reactant divided one solvent divided by concentration of the solute in other reactant, other solvent. Okay, that's it. Right? Okay. Write the question. Write this question. Iodine is dissolved and distributed. Iodine is dissolved and distributed. Iodine is dissolved and distributed in between. Iodine is dissolved and distributed in between CCl4 and water. CCl4 and water. Right? Iodine is dissolved and distributed in between CCl4 and water. CCl4 and water. 10 milliliters of CCl4 layer. 10 milliliters of CCl4 layer was titrated against 0.1 moles per cubic decimeter sodium thiosulfate. 0.1 moles per cubic decimeter sodium thiosulfate. Volume required was 20 cubic centimeters. Volume required was 20 cubic centimeters. Next one. 25 cubic centimeters of aqueous layer. 25 cubic centimeters of aqueous layer was titrated against 0.01 moles per cubic decimeter. 0.01 moles per cubic decimeter moles per cubic decimeter sodium thiosulfate. Sodium thiosulfate. Volume required was 10 cubic centimeters. Volume required was 10 cubic centimeters. Volume required was 10 cubic centimeters. Right. First question. Calculate the distribution coefficient. Calculate the distribution coefficient of iodine between CCl4 and water. Of iodine between CCl4 and water. Second one, what's the reason of using different concentrations of sodium thiosulfate for the titrations? What's the reason of using different concentrations of sodium thiosulfate for the titration? Okay, right. Shall we start? So you need to find the Kd of iodine between CCl4 and water, right? For that purpose, you need to find the concentration of iodine in both CCl4 and water, right? So how do you get this one? We can get sodium thiosulfate Na2S2O3 aqueous react with iodine goes to Na2S4O6 aqueous plus 2 NaI aqueous, right? So two of these are required, right? And don't forget to write that equilibrium I2AQ, I2CCl4 somewhere, right? You might get marks for this. Okay. So how to find I2 aqueous concentration, right? That is for the aqueous layer, right? So how to find iodine concentration? Sodium thiosulfate is 0.1 moles per cubic decimeter times 20 into 10 to the power minus 3 cubic decimeters. That is the number of moles of sodium thiosulfate. Then amount of iodine will be half of that. 2 to 1. Right? Then divide by the volume of aqueous layer. Right? So this is CCl4. Now I'll make it CCl4. Right? That is CCl4. So what is the volume? Volume is, we took 10 into 10 to the power minus 3 cubic decimeters. What's the value? Right? This cancels out to this one, everything, that is 0.1. That is 0.1. Right? Similarly, you can find I2 aqueous concentration. Amount of sodium thiosulfate is 0.01 moles per cubic decimeter into volume is 10 into 10 to the power minus 3 cubic decimeters divided by 2, that is the amount of iodine, into volume that you took was 25 into 10 to the power minus 3 cubic decimeters. Right? So this will become 50 and this is just 0.1. 0.1 divided by 50. We are not going to divide by 50. Instead of that, we multiply both by 2. Right? So that is 0.2 divided by 100. Right? 0.2 divided by 100 is 0.002 moles per cubic decimeter. Right? 0.002 moles per cubic decimeter. Okay? And they are asking the distribution coefficient of iodine in between CCl4 and water. CCl4 and water. Right? So the amount in CCl4 is 0.1 moles per cubic decimeter divided by water is 0.002 moles per cubic decimeter. How much is that? That is just 1 over 200. Right? So 5 into 10 to the power 3, right? Doesn't have any unit. Okay, right. Do it. No, this simply 50. No unit, simply 50. Okay, finished, right? So what's the purpose of using different concentrations here? Right? Uh, what's the purpose of using different concentrations? Right? When you are using, why we are using different concentrations? The thing is, we know that iodine is more soluble in CCl4. Right? Iodine is more soluble in CCl4 than water. Right? So if you use the same concentration, sometimes the volume of thiosulfate required for the CCl4 layer will be very high. You might have to put about 2 butyrates. Or for aqueous layer, sometimes by adding 1 or 2 drops, you get the color change, right? So that is why we are using different concentrations. That's right. As iodine is more soluble in CCl4, as iodine is more soluble in CCl4, as iodine is more soluble in CCl4, higher concentration of sodium thiosulfate, higher concentration of sodium thiosulfate is used to titrate the CCl4 layer. Okay, CCl4 layer, and lower concentration is used. Lower concentration is used to titrate. Lower concentration is used to titrate aqueous layer. Titrate aqueous layer. Okay. Right. Okay. So that's the reason of using different concentrations, right? It's obvious. If they ask what are the assumptions that you use, right? What are the assumptions that you use? The assumptions are temperature is constant and iodine is in same molecular form in both water and CCl4, and the system is at equilibrium, right? Those are the assumptions that you have made, right? Right. Another question. Next one. Iodine concentration in CCl4 solution is, iodine concentration in a CCl4 solution is 2 moles per cubic decimeter. Iodine concentration of a CCl4 solution is 2 moles per cubic decimeter. Two moles per cubic decimeter. 200 cubic centimeters of 200 cubic centimeters of this was added into 100 cubic centimeters of water. 200 cubic centimeters of this was added into 100 cubic centimeters of water. Two hundred cubic centimeters of this was added into 100 cubic centimeters of water. 25 cubic centimeters of 25 cubic centimeters of aqueous layer 25 cubic centimeters of aqueous layer was reacted with excess SO2. Was reacted with excess SO2. Was reacted with excess SO2. The resulting solution, the resulting solution was titrated against 0.1 moles per cubic decimeter sodium hydroxide. Resulting solution was titrated against 0.1 moles per cubic decimeter sodium hydroxide. Volume required was 20 cubic centimeters. Volume required was 20 cubic centimeters. Volume required was 20 cubic centimeters. First one, write balanced chemical equations for the reactions. First question, right? I'll write the questions here. Write balanced chemical equations for the reactions. Write balanced chemical equations for the reactions. Second one, calculate the I2 aqueous concentration. Second one, calculate the I2 aqueous concentration. Calculate the I2 aqueous concentration. Third one, calculate the remaining I2CCl4 concentration. Calculate the remaining I2CCl4 concentration. Calculate the remaining I2CCl4 concentration. Fourth one, calculate the distribution coefficient of iodine between water and CCl4 and water. Calculate the distribution coefficient of iodine between CCl4 and water. Between CCl4 and water. Okay, right. So that's the question, right? That's the question. And first part is you asked to write balanced chemical equation for the reactions. You asked to write balanced chemical equation for the reaction, right? So how to write the balanced chemical equation? First thing, what happens now when you take that aqueous layer out, right? When you take that aqueous layer out and reacted with SO2, what happens? This I2 aqueous react with SO2, right? And in presence of water, what it gives? It gives H2SO4 and 2HI. H2SO4 and 2HI. Right? H2SO4 and 2HI. Then what happens? You are titrating this with sodium hydroxide. You are titrating this with sodium hydroxide. So our H2SO4 react with one NaOH to give Na2SO4 plus H2O. Right? Similarly, HI, right, react with NaOH to give NaI plus water. Right? This is what happens. Right? Now, we need to have a relationship between sodium hydroxide and iodine. We need to have a relationship between sodium hydroxide and iodine. Therefore, we can, if you find that, we can directly do the calculation. Right? Therefore, I am going to add these two equations. Not two, all these three equations and get the overall equation. When I get the overall equation, you need to understand that there are two HIs. According to the first equation, there are two HIs. As a result, I have to multiply this third equation by 2. I have to multiply this third equation by 2. Once you multiply that third equation by 2, you can see HI cancels out, H2SO4 cancels out, and some water also cancels out, right? So the overall equation will be SO2 aqueous plus I2 aqueous plus 4NaOH aqueous goes to 2NaI aqueous plus Na2SO4 aqueous plus water. That's all. According to this, you can get the ratio. Right? you can get the mole ratio. What is the mole ratio? 1 iodine to 4 sodium hydroxide. 4 sodium hydroxide gives you 1 iodine. Right? So the first part, the second part, you can say directly you can calculate I2 aqueous concentration. How to find that one? Number of moles of sodium hydroxide. What is the number of moles of sodium hydroxide? 0.1 moles per cubic decimeter into 20 into 10 to the power minus 3 cubic decimeters. That is the number of moles of sodium hydroxide. Iodine will be 1/4 of that. Divide by 4. Right? Divide by 4. And what happens? The volume. Right? The volume that taken was 25. Right? 25 was the volume taken. 25 into 10 to the power minus 3 cubic decimeters. Right? 25 into 10 to the power minus 3 cubic decimeters. Right? So you get how much? 10 to the power minus 3 cancels out. Right? This is just 100. Right? This is 2. 2 divided by 100 is how much? 0.02 moles per cubic decimeter. Right? 0.02 moles per cubic decimeter. Okay, then what is the concentration of I2 in CCl4? That is the remaining concentration, equilibrium concentration, right? Originally it had this number of moles. How many moles? 2.0 moles per cubic decimeter into 200 into 10 to the power minus 3 cubic decimeters, right? We have this number of moles. Right? But in aqueous layer, we have how much in aqueous layer? Aqueous layer 0.02 moles per cubic decimeter into 100 into 10 to the power minus 3 cubic decimeters. You have that amount. Right? This is the amount originally that was in CCl4, and this is the amount that now in water. So how much of I2 in CCl4 remains? That is the original amount minus the amount in the aqueous layer. Minus the amount in the aqueous layer. Right. This is the number of moles of I2 remain in CCl4 layer. Divide by the volume of CCl4 layer, that is 200 into 10 to the power minus 3 cubic decimeters. That will give you the concentration. Okay. Right. So that is simply you can do a simple thing, something like this now. 100 into 10 to the power minus 3 cancels out from everywhere. So only 2 remains. This is 2 into 2 is 4. Right? So when that 100 cancels out, this is 0.02. 4 minus 0.02 is how much? 4 minus 0.02. This is 4 minus 0.02 divided by what here will be 2. 2 minus 0.01. That is just simply 1.99. Right? That is 1.99 moles per cubic decimeter. Then they are asking Kd. Right? What is Kd? Kd is equal to I2CCl4 divided by I2 aqueous. They are asking that is in between CCl4 and water. That is 1.99 moles per cubic decimeter divided by how much is the aqueous layer? Aqueous layer is 0.02 moles per cubic decimeter. Right? Almost like 100. $99.5. Okay. Right. Right. The subtitle: Users of distribution coefficient. Users of distribution coefficient. Users of distribution coefficient. Right. Put 1, 2, 3 and write the users, and one by one we'll discuss along with some questions based on those. Okay. Right. First one, solvent extraction. Solvent extraction. First one, solvent extraction. Okay. Under that, right? What do you mean by solvent extraction? That is what you are going to write. Under that, right? Extracting a solute. Extracting a solute dissolved in. Extracting a solute dissolved in one solvent into another solvent. Extracting a solute dissolved in one solvent into another solvent. Okay, this is what you mean by solvent extraction. Second one, second use, determining equilibrium constants. Determining equilibrium constants of reactions. Determining equilibrium constants of reactions. Right? That is, you can determine Kc's, Kp's, not Kp at all. I mean, Kc you can determine. Third one, determination of formulas of complex science. Determination of formulas of complex science. Determination of formula of complex science. Determination of formula of complex science. Okay, right. One by one, we'll see. Right, the first one, solvent extraction. Solvent extraction. Solvent extraction. Right. Solvent extraction. Now this solvent extraction, right, we'll see how we can extract nicotine from tobacco leaves. Right? Nicotine from tobacco leaves. Now what is this nicotine? Nicotine is an organic compound like this. Right? This is a pyridine ring. This is pyridine. Okay. this is connected to something like this, right? This is nicotine, right? I just square it. Right, this is nicotine, right? So it has a pyridinic ring, nitrogen, right? So this pyridine is somewhat harmful for people, okay, right? So however, what's happening now, this one we are going to extract from the tobacco leaves, right? So the tobacco leaves, we have this. So what we are going to do, we are going to react this particular, we take the tobacco leaves and crush it. You can put it into a blender and blend it, right? So you are breaking the cells into pieces, right? And you get a pulp like something. And what happens, you can react that one with HCl. You can react that one with HCl. Once you react with HCl, what will happen? This will form a bond with hydrogen and Cl minus. You get something like this, right? You get something like this. So this is an ionic compound and it is readily soluble in water. It is readily soluble in water. So what happened? The entire compound will dissolve in water. Okay? Entire compound will dissolve in water. Right? So now what happens? In water, you have this nicotine dissolved. Right? Now you can filter off all the unwanted material. Right? You can filter off all the unwanted stuff. Right? And take the aqueous layer. Right? To this aqueous layer, again, we add NaOH. Right? When you add NaOH, what will happen? This part is neutralized and again it will convert into pyridine. Right? This one pyridine ring will be restored. Right? And now it will convert into the original nicotine. Right? It converts into original nicotine. Right? Now when it converts into original nicotine, this is slightly insoluble in water because of this whole organic part. Now earlier it was ionic, now it is not like that. Therefore, it's like this now. Right? It's like this. Then what happens? You can put some organic solvent into that. You can put some organic solvent into that. Right? So when you add CCl4 like something, what will happen? The entire nicotine will move into the CCl4 layer. Right? But some amount will remain in the aqueous layer. However, most of the nicotine will move into the CCl4 layer. Thereafter, we can evaporate the solvent and get the nicotine back. Understood? Right? So that is what we are going to do. So originally, nicotine dissolved in water and we can't just heat water. Why? If you just heat water, what will happen? The nicotine will also evaporate. And also there will be some structural damages and everything. Right? So in order to overcome that problem, what you can do, you can extract this one into something like CCl4. Right? And CCl4 is more volatile than these compounds. As a result, once you get this solute into CCl4 and allow to evaporate, what will happen? In that case, CCl4 evaporate faster. Right? And only nicotine will remain. Right? Shall we write that? Okay, just write. Extraction of nicotine from tobacco leaves. Just write. Nicotine is insoluble in water. Nicotine is insoluble in water. It contain pyridinic nitrogen group. Contains a pyridinic nitrogen group. Contain a pyridinic nitrogen group. Next point. Crushed tobacco leaves. Next point, right? Crushed tobacco leaves are reacted with diluted HCl. Crushed tobacco leaves are reacted with diluted HCl. Where HCl react with nicotine, where HCl reacted with nicotine to produce a water soluble compound. Produce a water soluble compound. Right. Water soluble compound. Right. So we draw this one, nicotine. Just write nicotine. Right. Next point. Filter off the solid matter and separate the aqueous layer. Filter off the solid matter and separate the aqueous layer, which contain soluble salt of nicotine. Which contain soluble salt of nicotine. Add sodium hydroxide. Next point. Add sodium hydroxide into the resulting solution. Add sodium hydroxide into this resulting solution so that the salt will again convert into nicotine. salt will convert into nicotine. The resulting solution contains aqueous solution of nicotine. Aqueous solution of nicotine. Point. Add a suitable solvent like CCl4, and a suitable solvent like CCl4, and allow to reach the equilibrium, Okay. Next one. Separate the CCl4 layer. Separate the CCl4 layer and nicotine can be separated by evaporating the solvent. Nicotine can be separated by evaporating the solvent. Right? So what we're going to do now, we take the this part, crushed everything with HCl, soluble salt of nicotine. When you add sodium hydroxide to that, you get nicotine in the aqueous layer. Now we are going to add CCl4. It's like this, right? We have something like this, which is known as separation funnel. This is called separation funnel. Right? The separation funnel, it looks like this, better than this, of course. Right? It would look better than this, however. Right? So what happens when you add these two solvents? This is CCl4 and this is water. The layers get separated, right? And what will happen? Nicotine will be distributed in between these two, right? But you know that nicotine is an organic compound, less soluble in water, right? Mostly it will move into the aqueous layer. Move into the CCl4 layer, right? Then what will happen? Once you have this, we allow to separate, and you can understand that by just opening the tap, you can separate the CCl4 layer, right? So this is called separation funnel. Right? We call this one separation funnel. Right? From this, we can carefully separate the CCl4 layer. Right? This is the CCl4 layer. and what we're going to do, we are going to allow to evaporate. You just can place it in a slight heat, right? And finally, you can get the solid nicotine there. Right? Solid nicotine there. Right? So this is one of the methods that we use. Right? These methods are really important. Right? Very useful methods. Right? And you know that some drugs are there. Cocaine. Right? Cocaine is extracted from coca leaves. Right? Some of you might have seen coca leaves. Right? It also identical to the sandalwood leaf. Right? The tree is similar to sandalwood. Right? And you have two veins going like this in the coca leaf. Right? You might have seen. Right? So the cocaine is extracted from these coca leaves. Right? In order to extract little amount of cocaine, we need to have very large amount of coca leaves. Right? Because the amount of compound that you have in a leaf is very small. Right? So few milligrams, you need to have about 5-10 kilograms of leaves, right? And you can use the similar procedure and extract. You can use the similar procedure and extract, right? So those drugs, right, are really expensive, right? Those drugs are illegal stuff. Those are really expensive. Why those are really expensive? Because in order to get a little amount, very little quantity, you need to have a very large amount of leaves, the plant material. Okay, so they need to grow it, right? So in order to grow, what will happen? They have to do it very secretly, and they need a lot of land, right? So you can't have very large area of land very secretly, right? It's very difficult, right? And also in order to do this procedure, you have to be an expert, right? Just you can't extract, right? Because if you do a little mistake in this procedure, what will happen? It will decrease the yield. Sometimes you might not get anything at all, right? So you have to do it very professionally, right? And then only you can get the product, right? So and it takes some time, right? It takes some time. Just you can't do, right? That is why those are really expensive, right? So that is also done using this. Okay, right. Shall we write this one? Got it right? Okay. So that is about solvent extraction. And you need to know one thing. That is, when you are finding the suitable solvent, right? When you are finding the suitable solvent, this Kd is really important, right? Kd is really important, right? Just consider this situation. We take Kd of nicotine, I say NiC, CCl4. I am just giving some values, right? These are not actual values. I am just giving some values. Nicotine in between CCl4 and water, right? Let's say this is like 10 to the power 3. I'm just saying, right? And the Kd of nicotine in CHCl3 over nicotine aqueous, right? So if that is 10 to the power 4, which one is more suitable, right? CHCl3 is more suitable, right? If it is like this, we know that CHCl3 is more suitable. Why CHCl3 is more suitable? Because you can extract more nicotine into organic layer, right? That is really important, right? Next point. When choosing a suitable solvent, for the extraction process, distribution coefficient is important. Distribution coefficient is important. Distribution coefficient is important, right? Just write Kd1, nicotine CCl4 over nicotine water is 10 to the power 3. Kd2, nicotine CHCl3 over nicotine aqueous or water is 10 to the power 4, right? So what is the best solvent? This is the best one. CHCl3 is the most suitable solvent. Okay, right. Most suitable solvent. And also we have something like this. Now suppose we have, just think about, 100 cubic centimeters of aqueous layer is there. 100 cubic centimeters of aqueous layer is there. In order to add into that, we take 100 cubic centimeters of CHCl3. Right? We take 100 cubic centimeters of CHCl3. What we are going to do, we are not going to add entire 100 cubic centimeter into this one and get extract. Right? We are not going to add entire 100 cubic centimeters at once and extract. Right? What we are going to do, without doing that, first we add 50 cubic centimeters of CHCl3 into this and extract nicotine into 50 cubic centimeters. Okay, extract that into 50 cubic centimeters. Separate it and get the resulting remain aqueous layer. Right? Remain aqueous layer. Still 100, no? Remain aqueous layer. Then what you're going to do? Then we are going to add the remaining 50 cubic centimeters of CHCl3 into this and extract. Right? Rather than adding everything at once, we are going to add that entire volume as two 50 cubic centimeter portions. Once you do so, what happens? You can extract more nicotine into that entire 100 cubic centimeters. Right? If you add it at once, you get less amount, but if you add them as parts, you can extract more. Okay? Right. Just right. Rather than adding entire volume of rather than adding entire volume of the organic solvent at once, rather than adding entire volume of organic solvent at once, adding it as several parts, several portions, using successive extraction, can extract more nicotine, into the organic layer, can extract more nicotine into the organic solvent. Okay, so that way you can extract more nicotine into the organic solvent. Right. Okay, we'll write a question, we'll do a question and do that part, right, and see whether it is possible or not. Right, just right. The distribution coefficient of nicotine in CCl4 and water is 100. In CCl4 and water is 100. Hundred cubic centimeters of water contain 10 grams of nicotine. 100 cubic centimeters of water contain 10 grams of nicotine. It is proposed to extract nicotine into 100 cubic centimeters of CCl4. 100 cubic centimeters of CCl4. Calculate the mass of nicotine. Calculate the mass of nicotine that can be extracted into CCl4 First one, by using entire volume at once. Second one, by using two successive extractions, 50 cubic centimeters each. By using two successive extractions, 50 cubic centimeters each. Okay, right. Shall we start? Okay. Now, the first situation. First situation, you had 10 grams of nicotine in the aqueous layer. There was 10, right? And CCl4 was added into this one. CCl4, right? CCl4 was added into this, and this is water, right? In that case, how can you do this one? Now, in this case, you don't have to convert this one into number of moles. Remember that, right? You don't have to convert this one into number of moles, right? Why? Because you just can do with the mass, right? First, we'll calculate it with number of moles, and then we'll see, right? Then we'll see, right? So you had 10 grams, right? 10 grams. Suppose the amount moved into the CCl4 layer is X. So now in CCl4 layer, you have X grams. CCl4 layer, you have X grams. So what is the equation? Nicotine aqueous has an equilibrium with nicotine CCl4, right? Just write that equation because the equation carries some marks, right? Sometimes it carries some marks, right? So what we are going to do, we are going to apply into this equation. Right? Now what happens? We know that KD is equal to, write the expression nicotine CCl4 over nicotine aqueous. Okay. So what is the nicotine CCl4 here now? It is X. That is the mass. Mass divided by molar mass of nicotine. Mass divided by molar mass of nicotine. Right? That is the number of moles. Right? That is the mass is X divided by molar mass. That is the number of moles. And this divided by volume. What is the volume? Volume is 100 into 10 to the power minus 3. 100 into 10 to the power minus 3. Got it? 100 into 10 to the power minus 3. This is the concentration of nicotine in the CCl4 layer now. Right? Divide by nicotine in the water layer. How much in the nicotine water layer? 10 minus X is the mass. Divide by molar mass is again M into 100 into 10 to the power minus 3. Right? And this is equal to how much? 100. Right? If you carefully go through, you will understand that this molar mass cancels out. The 10 to the power minus 3 stuff also cancels out. Right? And here, as the volumes are same, volume will also cancels out. Right? If the mass is given, you don't have to convert it into moles and concentration. Because both we have the same, in both layers we have the same solute, right? So the number of moles definitely cancels out. Molar mass will cancels out, as well as this 10 to the power 3 also cancels out. And the volume sometimes will remain. If the volumes are different, it will remain, right? The volumes I can't say, right? Though the volume cancels out here, I am not saying that volume always cancels out. It's not always cancelling out. But the molar mass still cancels out. So you don't have to convert that one into volume, number of moles, right? So simply it is 100 is equal to X over 10 minus X, right? 100 is equal to X over 10 minus X. So what is the value of X? To simplify this one, the value of X will be, this is 1000 and this will be 100x. When it comes to this side, 1000 divided by 101, right? 1000 divided by 101. How much? 99 point, sorry, 0. 1000. That is 9.901 grams. This is the amount that you can extract. X is the value, no? Okay. So that is the amount that you can extract into the organic layer. Right? You don't have any issues. Right? Okay. Shall we do this one? Right? Quickly write that. Got it, right? So you can extract how much? 9.901 grams, right? So almost everything is extracted, right? I'll write it somewhere, right? Oh no, I'll write it here. 9.901 grams extracted with entire 100 cubic centimeters at once, right? So if you get that amount, you don't have to do it separate, right? Because you are getting almost everything, no? Right? Shall we do the next one? Right? Okay, next one, right? I'll erase this part and start again. Okay, next one. Similarly, we had 10 grams in aqueous layer when you had CCl4, but here it is 100 cubic centimeters, here it is 50 cubic centimeters. Okay. Suppose the amount that move into the aqueous layer, CCl4 layer is Y. Suppose that amount move into the CCl4 layer is Y. Okay. If it is Y, we can get that KDE. Don't have to write the expression again because of we have already written that one. How much? Y divided by 50 over 10 minus Y over 100. Right? What is this 50? Volume. 100 volume. Right? Aqueous layer is 100. Right? So that is 100 equal to this 50 and 100 cancels out. This is 2. That is just 2y over 10 minus y. 2y over 10 minus y. Right? So what is y? Y is equal to, this will be 1000 divided by 102. 1000 divided by 102. How much? 9.804 grams. 9.804 grams. That is the amount extract. 9.804. right? Okay. So what is the amount remaining now? We have to go to the next one now. Amount remaining. Amount remaining 10 minus 9.804. Right? 10 minus 9.804. 0.196 grams remaining. Right? 0.196 grams remaining. Right. So what is happening in the next one? We take 0.196 minus Z goes to the CCl4 layer. This is Z. Right? 0.196 remaining. Right. So what is KD? KD is equal to again Z over 50 over 0.196 minus Z over 100. Right? So this is 100 equals to 2Z divided by 0.196 minus Z. What is the value of Z? 19.6 divided by 102. .192. That is the amount that you can extract. Okay, 0.192. So what is the total amount that you can extract? These two, right? Total nicotine that can extract is how much? 9.804 plus 0.192. That is 6,999 grams. See, earlier it was 9.901 grams, but now it is 9.996 grams, right? So you can extract more nicotine there, right? You don't see a difference because these values are extremely, big. 9 out of 10, 9.9 is okay now. But here you can understand that you can extract more. Okay? Rather than using everything at once, if you use in parts, you can extract more nicotine. Right? Okay. Shall we write? Correct, right? Not that difficult. Okay. And when you are doing this successive extraction, right, we are going to do a calculation saying that about fraction remaining, right? So that will be much easy rather than doing this one. Okay. And on next class, we are going to do some calculations like that, right? So this lesson is not that very long lesson, right? We have already covered almost everything, right? Maximum another 1 day to cover the stuff, and most probably another 2 classes, right? Another 2 classes we can do some questions, right? Not most probably, next day we are going to finish this one, and the following day we can do some questions and complete this session, right? So these are really easy sessions, right? So you can score marks, right? So we'll do the lesson in next class. Okay.